This is section 5.8, polynomial models in the real world, and our objective is to fit data to linear, quadratic, cubic, or quartic models. And what we're going to focus on today is the n+1 point principle, and it says for any set of n+1 points in a coordinate plane that passes the vertical line test, there is a unique polynomial of degree at most n that fits the points perfectly. And so what we're talking about is, like, if you have 2 points will determine a unique line. If you have 3 non-collinear points, you'll get a quadratic, a parabola. You can get a unique parabola degree 2. And if you had 4 points that were non-collinear, you would get a cubic function degree 3. So given as many points as you have, you can subtract 1 to come up with a unique polynomial. So let's look at problem 1. It says, what polynomial function has a graph that passes through the points? And they give us 4 unique points there. And so since there are 4 points, we're going to take 4 points and we're going to subtract 1 from that, and you're going to get a degree 3. So we were able to come up with a polynomial, a cubic polynomial, degree 3, that passes through those points. And here are the steps you're going to follow. So again, here step 1 says by the n+1 point principle, there is a cubic polynomial that satisfies the 4 points. And then what we're going to do is we're going to go to our graphing calculator, and we're going to do regression on our calculator. And we've done linear regression before, we've done quadratic regression. This time, since we want a cubic polynomial, we'll do cubic regression. So under stat, L1, you're going to put in your x values. L2, you put in the corresponding y values, and then you go back to stat, calc, cubic regression, and I'll show you a quick video on what happens when you do that. Okay, so here we have the calculator. I'm going into stat, again edit, and I'm going to clear out my L1 and L2. Again, I just highlight L1 and hit clear enter, and L2, clear enter. Clean those out, and then we're going to put in our ordered pairs. So in L1, I'm putting in my x values, -2, 0, 1, and 2. And then I'm going to go over into my L2 and put in the corresponding y values. So I will have 13, 9, 4, and 5. Once I put in all of my ordered pairs and double check that they're correct, I go back to stat, calc, and at this point I'm going to pick cubic regression because we want a cubic polynomial, and I hit enter through this, and I will get my coefficients of my cubic polynomial. One thing I want to point out to you here is look at your b term right here. This is scientific notation, so it's 9.7 times 10 to the -13. That's essentially 0. So that means I'm not going to have an x squared term when I write out my cubic polynomial. So my answer here for this would be y equals, my a is 1, so 1x cubed. We said b was 0. C is -6, so -6x. And then my d, my constant, is 9. So this is the cubic polynomial that closely fits those 4 points. Okay, so for problem 2, it says, what is a linear model that best fits this data? Use the model to estimate the egg consumption in 1995. Here it's actually telling us what model we want to use. It's saying use a linear model, so that means I want degree 1. We're not going to use the n+1 point principle. We technically have 4 ordered pairs here in this table, but it's stating use a linear model. So when you're doing your homework, if it tells you exactly what type of model you should use, then use the appropriate regression based off of that. Here I'm going to do linear regression. If I don't tell you, either on a test question or a quiz question, then you'd want to use the n+1 point principle. So in this case, if it didn't say linear, you'd go cubic because there's 4 points. Now, when you have years, we're going to let x be our number of years since 1970. And that's something we've been doing for a while here. So this will be 0, then 10, 20, and 30. So these will be my x values. That's what I'll put in L1. And L2, I'm going to put in my y values, my egg consumption. So we have 4 ordered pairs there. So once you do that, you're going to select linear regression when you go back to Stat and Calc, and you're going to get the line y equals negative 2x plus 291.5. The calculator will give you all of those values. Now, this is where the real-world application comes in. We're going to use the model to estimate egg consumption in 1995. So, based off of this model, in 1995, x would equal 25. So we will replace x with 25, and we will get an estimate of 241.5 eggs, and we'll round that up to 242 eggs. You wouldn't want 0.5 eggs, so that's what we can estimate in 1995. Okay, so this next problem on the back side says, what is a quadratic model this time that best fits the data? So this time now we're going to go degree 2, quadratic. Okay, and it's the same values that we had on the other side. So we'll use quadratic regression, and you're going to probably have that data already in your calculator, so we don't need to change anything there. And what we're going to do, again, this is 0, 10, 20, and 30. We're going to put stat calc quadratic regression, and it'll come up with this quadratic model. Y equals 0.13x squared negative 5.9x plus 304.5. And again, now we're going to estimate our consumption in 1995. So x again is 25 in 1995. So we'll replace x in this equation with 25. And we're going to get a value when you calculate that to be y equals 238.25. So in this case, we'll say 238 eggs. So it's slightly different than what we had before. In problem 2, when we did linear regression, we estimated 242, and with quadratic, we're estimating 238 eggs. Okay, for the last problem here, problem 3. Is the linear or the quadratic model better for estimating egg consumption between 1970 and 2000? Which is better for extrapolating egg consumption beyond 2000? So to do this, we need to understand the difference between interpolation and extrapolation. Interpolation, first of all, you use that when you're estimating within the domain. So our x values are going from 0 to 30. So if I'm within the domain, I would want to use, you're using interpolation, and that's usually reliable. Outside of the domain, we use what we call extrapolation, and that becomes less reliable the farther away you move away from the data. So when we're doing this, we need to actually look at how closely either our line or our parabola follow the ordered pairs that we have. So these are the steps you're going to want to do. We're going to need to do a stat plot. We want to plot those ordered pairs. So on your calculator, you want to make sure you turn your stat plots on so you get that discrete graph of your ordered pairs. And then we're going to fix our windows so we can see. I'm going to put x min at 0, x max at 50, y min at 200, and y max at 400. If I don't do that, you're not going to see what you want. And then I'm going to go and y sub 1, I'm going to put in my linear model, and y sub 2 we're going to put in our quadratic model, and then when we hit the graph, we'll be able to see how closely either of those models fit the data. So I'll show you a quick video of that. Okay, so here I am showing you that you go to second stat plot. If you haven't have it on, turn it on right here, just toggle it on. Here I've switched my windows, I put in my y1, y2. And if you graph, what I want you to notice here is that you can see the parabola follows the data closer than the line does. Okay, and so that's what I want you to key into. The parabola, the quadratic model, is a better model for the data. And basically, what I would say with either of these, though, is that both models are fairly unreliable. We don't have enough data here to really be able to tell what's going to happen in the future. We only have forwarded points. The more data you have, the more accurate you can rely on your model. So that was lesson 5-8, polynomial models in the real world. Good luck.